Hi, and welcome to the fourth statistic lecture. This is the last of the statistics lectures that I will be giving. So last lecture I talked a bit about the hypothesis testing, and more specifically I talked about the t-test and also the chi-square test. And then we also covered something or a bit about p-values and confidence intervals, and also an example of hypothesis testing. Um, In this lecture, I want to cover correlations, power analyses, and sample sizes, and how to calculate those. So there are different ways to do that. So to start off with, we have correlations. And what is correlation? Correlation, it is a statistical measure that expresses the extent to which two variables are linearly related to each other. So that means that if they change together at a constant rate, and it's a common tool for describing simple relationships without making statements about the cause and effects. And so how can we determine this or calculate this? So typically one of the ways to do it is we can plot it in an XY graph or scatter plot. So then we'll have the different dots, and there's also we can also calculate the coefficients for those. So for example, we have Pearson correlation coefficient, which is a coefficient that we usually use for linear relationships. So that's when you have like an x and a y, and then you can plot those, and you can draw a straight line through the middle of the points. And we also have another one called Spearman correlation coefficient, which is very similar to the Pearson, but it's just for non-parametric ones instead. But yeah, as I said, we can plot them in a scatter plot, which you can also see here. So if we start with at the bottom ones, there's 4 plots. So we can have if r is equal to 1, so plus 1, that means that the that means that when we go 1 out on the x-axis, we also have an increase in the y-axis. And if it's 1, it's a perfect correlation, so the line that you draw through the points, it goes directly through each and every single one of those. If it's close to 1 and not perfectly 1, then there might be a strong association between the two different values or variables. So that's also what you can see here in the graph or the scatter plot, where we have the different points very close to the line, the straight line, but not exactly on the line. So that's a strong association. Then you can also have it close to -1. So here, instead of the points going upwards or the straight line going upwards to the right side, you have it going the other way, so it goes downwards. So when you go 1 out on x-axis, you'll have a decrease in the y-axis. So when it's close to -1, so that's also what we see here under the perfect one, there could be a strong negative association, so that it decreases with x. And then if it's close to 0, also if r is close to 0, so the correlation coefficient, then it means that there is a weak or no association. So that's also what you can see here on the plots, the different dots that just scattered all over the place, and you can't really make a straight line through everything. Then we also have the correlation coefficients. So as I said before, if it's 1 or if it's positive 1, like exactly 1, then it's a perfect correlation that increases, and if it's negative, then it's decreasing. So that's also what we see in the plots at the top. So if we start from the left side, we have -1. So it's a perfect decrease of perfect correlation, but it's decreasing. We have a bit less than 1, -1 still, a bit less than -1. Then there might be a medium or a strong association, but it's negative correlation. Then we have the zero correlation, which is basically everything just scattered all over the place. Then we have the medium positive one, where the numbers of the correlation coefficients is positive. And then we have the +1, which is the perfect positive one. So here you should also keep in mind, I think it's in the first lecture where, or maybe in the second lecture where we had the visualizations, we also had the scatter plots. If you remember, there was a dinosaur in one of those scatter plots, so that would have a correlation of 0, but there might still be some kind of association between those variables. So that's something you have to keep in mind. And here we just have a small graph for the correlation causation association, or not graph, but a little, I would say, comic strip. So a guy, he is like, oh, there's another huge study found no evidence that cell phones cause cancer. And then you have the professor or something, someone saying, I think that's just got it backwards. And then he shows a graph with the US cell phone users and total cancer incidence, and then say, just to be safe, I want to see more data. Then I can maybe assume, or I'm going to assume that cancer causes cell phones instead because of that. So that's something we have to remember. We always have to know what we want to look for and what the different variables are or mean. So that's also something we can see here. So if we just randomly take two variables, for example, the number of people drowning by falling into a pool and films Nicolas Cage appeared in, then you might see a trend, but it could mean nothing, even if it got a correlation. And here, this slide is just to show quickly the formula for calculating the Pearson's correlation coefficient. So you would have two variables, you would have x and you would have y, and then you would have the sum of the difference between the different points and the mean for both the x points, or for both the x variables and the y variables. And then below you would do the same, but you would do it with squared and also with the square root, and then you will get Pearson correlation coefficient. So that's for the linear ones. Usually these computed using a computer or any software. So that could be from R, it could be from Excel, it could be from Python, or a third one. So now we'll move into power. And the power of a test is linked to type 2 error, which we also talked a little bit about in the previous lecture. So if you remember, we had this example with the not pregnant, maybe pregnant lady. And we also had our table with the false and rejected and null hypothesis and everything. So for the type 2 errors, that was the false negatives. More specifically, that is when we do not reject the null hypothesis when it is actually false. And we usually denote that by the probability beta. And the power is then, or the power of the test is then 1 minus beta. So beta is typically 20, and then the power will be 80%. So why are we usually so interested in the power and power analyses? So when we design our studies, we always want a good power. So that means that we have a good chance of detecting the true positive clinical relevant effect. And typically, as I said, the power is at least 80%. That's what we deem good. And then we can even have a higher power for example, 90% or something like that. And there's multiple reasons for that. So, or the reasons is that it is ethically irresponsible if you don't have enough power, or it can be at least, and it's also a wasteful of time and resources. So, for example, if you undertake a clinical trial with only 40% chance of detecting a real treatment effect, then maybe the patients would have been able to get another treatment which was actually working, which would then be ethically irresponsible. Um, so because then you actually wouldn't be able to see if there were any effect or not from the drug, maybe. It would also be a waste of time and resources because usually it takes a long time to conduct these clinical trials, and it also takes a lot of resources from a lot of people and also a lot of money to do. So that is why you always want to make sure that you have enough power in your studies to actually provide some results that you can use for anything. So there are several factors that can influence the power of the test. Typically, so as I said, the power that is when we detect the true positives, and that's one of the very important things that we want to do with our studies. Um, but we have some factors that influence that, and one of those factors is the sample size. So the amount of patients that we have that we're testing on or conducting our trial on. So with an increasing sample size, the power will typically also increase, and that is due to the ability or greater ability to detect the changes in the clinical effect when you have a larger sample size, because you are doing the measurements in more people. And typically that can then also shrink or make the confidence interval smaller, because you have more people that you're testing on, and hopefully the measurements is maybe similar to each other. But again, if you have too many sample or too many in, like that you're doing the test on or doing clinical trials on, then that might also be a waste of time or resources, because if you only need 10 people, for example, to see that you have an effect, and then you are conducting a trial on maybe thousands of people, then that is a waste of time and resources, because you could have spent a lot less money on the same trial. So to calculate the sample size and the power calculations, there are different ways to do that. So to calculate the sample size, and we will here in these slides go over the Altman's nomogram and also Liang's formula, which are two fairly easy ways to calculate sample size. In some situations, it is necessary to use more general or complex formulas, but usually you have computers to do that, or you're calculating using computer software. So for example, you could do it with Excel, you could do it with Python, you could do it with R. Um, there's also online websites where you can do that or have a good estimate of the sample sizes. So there are some options to do. So if we start with Altman's nomogram, so Altman's nomogram, it looks like this. You have this table, or not table, but you have this figure with standardized difference on the left side, and then you have the power on the right side. So this is a very easy to use diagram, which is appropriate for various tests. It is used to estimate the sample size for two equal sized groups. However, one requirement for the nomogram is to calculate the standardized difference, and there are formulas to do that, which I'll also go through. So here we have the standardized differences. We have a table with the different hypothesis tests and how the standardized differences can be calculated for those tests. So the standardized difference, it's the difference in the mean of a variable between two groups, divided by the estimate of the standard deviation for the variable. So this is very closely related to the smallest difference in the mean, which we think is clinically important. So that's also the delta you see in the terminology. And then you have the standard deviation, which is the sigma, which is also in the standardized difference formula. So those are very important. For the chi-square test, here we're dealing with proportions instead. So here we have, instead of the smallest difference in mean, which is clinically important, we have the differences in the proportions between the two groups. So this is something that we use when we have to use Altman's nomogram. For the Liang's formula, it's also very easy to use. It's a quick formula that can be used for sample size calculations, and it can only be used for unpaired test or unpaired t-test and chi-square test. So that's the chi2 test. If we're assuming 80% power, and that is two-sided significance, a significant level of 0.75, then the formula will be sample size equal to 16 divided by the standardized difference to the power of 2. So that's actually the same thing that we also had in the table with the different formulas. Just remember to only use it for unpaired t-test and chi-square test. If you then have a power of 90% instead of the 80%, then the 16 will have to be changed out with 21. So this have something to do with how you calculate the different values that accompanies this, and it uses the power or the beta. So that's the 0.2 if it's 80%, and it also uses alpha, and they look at the set distribution and the different values under that. So that's how they get the 16 and 21. So here we'll go through an example of how to calculate the sample size. So we'll first have it for unpaired t-test. So imagine that we want to examine the effectiveness of a medication, and therefore we need to recruit some patients for this study that we want to do. We want to look at the outcome duration of oral source, and we want the power of 90% and with 5% level of significance. And then we think that the duration or the clinical important difference in the duration of oral source is 2.5 days, difference in the mean duration. And then we know that there's a standard deviation of 5 days. So therefore we have two different groups. The two different groups are independent groups. We have a group that takes the medication, and we have another group that doesn't take the medication. So first off, we try to use the Altman's nomogram to do this. We calculate the standardized difference first. So we said that we had 2.5 days, which was the clinical important, the minimum clinical important difference that we want to see. And then below that, we have 5 days standard deviation. And this then turns out to be a standardized difference of 0.5. So then if we use the Altman's nomogram, we draw a line from the 0.5 that we just calculated in the standardized difference. So that's on the line on the left side. Draw a line to 90% power that we want to use, or we want this study to have. And then we can see that we need approximately 160 patients according to this diagram. And that means that we'll be needing 80 patients in each group for the power to be 80% or 9%, sorry, with the 0.05 level of significance. And we can also use the Liang's formula to calculate the needed sample size in each group. So same with Altman's nomogram, we also have to use the standardized difference. So here we said that we wanted a 9% power, so that means that we needed to use the 21 instead of the 18. And then below that we have the standardized difference, which was 0.5. We take that to the power of 2, and then that gives us that we need a sample size of 84 patients in each group, which means that we would need a total of 168 patients. And this is also very similar to Altman's nomogram, so they are very similar to each other. As I said, there are also online tools that you can use to calculate sample size. So for example, we have calculator.net, which can help with calculating the sample size by inputting the confidence level that you want to have, which here is 95%, and the margin of error, and then some population proportions, and then the population size that you would have if you could select as many as you want, and then that would then spit out a number of patients that you would need to have in your study. Likewise, there's, for example, clean calc, which where you can here actually select what kind of study group design that you have. So if you have one group versus the population, or two independent groups, and you could also select what kind of endpoints, so that's what kind of outcomes do you have. So is it a yes, no, or is it continuous variables? So these are very good and very, oh, they can help you a lot by with calculating the sample size. So for example, if we then take the clinical cal, they can actually give you an example of how to use that tool. So if you see on the left side, you can pick like what kind of study group it is. So it's the group design, you have the endpoint. So if you, for example, have two groups with the yes/no endpoint, then you have to give the anticipated incidence. So how much do you think there will be for incidence, and then also the enrollment. So that's a number of patients in each group. So for example, if you say for each group 1 patient, I want two group 2 patients, then they will also take that into account. You have to give in the alpha and power, so that's the 0.05 and the 80% power that we usually use, and that's for the type 1 and type 2 error rates. And then that will spit out the sample sizes that you need for each group. So in this one on the right side, we have the sample size of 690. So that's the enrollment of 1 to 1. If you would have 1 to 2, then you would have a bigger group 2 than in group 1. And likewise, if you had other numbers. It will also give you the study parameters, so the percentages, the alpha, beta, and power. And it will also show you the power calculations that you use to calculate the sample size that you need. So they have the formulas, and then how they use the formulas, and also the different what each of the things in the formula means. So this is very good. And it can also help you in calculating sample size if you need. So yeah, this is the end of the 4th lecture. I hope it has been helpful with the slides and me trying to explain it. And if there's any questions for the content, you feel free to ask both at the seminars and emails. The emails should be in the first page or the first slide, and also in the CPS101 manual. And for the assignments, if you do the assignments, you should be able, that should cover all the topics that we have gone through. So if you manage to go through those and calculate those, then you should have a good grasp of the different topics. In the assignments, there's also, or there will be a flowchart of other hypothesis tests that can be used, but not that we have necessarily learned about them yet in this course. So maybe that's for the future. But otherwise, good luck.